Okay. Well, as a fun update, the last video I recorded ended up being too long, which is like, I've seen hour-long videos. How is my 16-minute video too long? It's probably because I'm on my iPad right now. But so I just split it up into the two theorems that I was looking at. But here's our next one, and this one's a bit of a doozy. Um, it's probably going to be extremely long. The original proof that I have in my flashcards is quite long, if I recall correctly. This is the one that utilizes the division algorithm, which I guess I could like have a Euclidean geometry or not you whoa, oh, not Euclid, the Euclidean algorithm video, but the division algorithm um is the whole right. How do you say it? Like some in well, why can't I write? Oh, that was weird. In, if it's not if it's a multiple of something. Wow. Oh no, my pencil's being weird. Is it as tired as I am? So like n is a multiple of m right here because it's times some number q, right? But if we have a remainder as well, this is like a standard division problem where you have, n is a multiple of m, but there's like this remainder. So if you were to get rid of the remainder, then it'd be a multiple. So we can use that fact. And it looks like we'll have to use it in this proof actually. Wow, my pencil's being weird. Maybe I should stop for the night. Maggie texted earlier and was like, I hope I didn't wake her up. I'm so scared. I've been sending these in the group chat as just like little nuggets for you guys to wake up. I'm gonna not send anymore, and then in the morning I'll send like the remaining like three. I'm hoping this is the last one, but honestly, if I'm still, not able to fall asleep after this, yeah, maybe I'll record more. But another short theorem, a subgroup of a cyclic group, is also cyclic. So what we have to show here, initially when I saw this, I was like, oh, it's just subgroup test. But no, we're given that a subgroup already exists, and that it's a subgroup of a cyclic group. So let's start there. Let G be cyclic. Wow, I'm getting really tired. Cyclic. Uh, I I'm saying that A generates G, um, and H be a subgroup of G. Great. So our goal is to show that H is also cyclic, so that what does that mean? So I just kind of described it here, but we want to show that there's some value in H that generates H. Um, so let's how do we want to start this? Um, let's go with our definition of cyclicness so far. Since A generates G, um, we know that. How do I want to say this? Let's use a to the n like we normally do. I'm gonna go to the next line. A to the n is nh, which is true. This is like any a to the n, and so um, now we're gonna be. Oh, and I don't want a period for some. Normally, n is an integer, and it still is technically, but it's a positive integer now. I'm not. I tried to theorize why this is the case. My assumption is no, because H is a subgroup. Oh, I was going to say that I don't know why n has to be positive. Maybe it's just to make it simpler, so we're not having to consider negative, but it's definitely useful for this next bit. Um, we're going to show, or we're going to claim something, kind of like, and assume this, and if we get a contradiction or whatever, right? Um, so we're going to say that um, that there is another integer. So let m be the smallest integer. I'm gonna just write int, because I'm lazy, in z plus, such that a to the m is an h. So we said that a to the n is an h for all of these positive integers. We're going to say that m, and this is m as in marshmallow, is the smallest one. So typically you would think this is probably like a to the first power, but we don't know. This is all abstract. This could be 37 for all we know. So we're going to claim now that this generates this h. We claim a to the m equals h. A to the m generates. I think those are equivalent. I'm just writing them both because I want to be safe. So now, how do we show that a to the m does generate h? Well, as I've shown earlier, and we've had experience with cyclicness. Ooh, whoa, sorry about that. I just shifted. Um, we will show this, or we must show then that for all B and H, um, B equals like some power of A to the n. So this gets us a little confusing. I believe the textbook like has A to the m equals C. I don't like that. I find that confusing because I'm like, well, where did this C come from? So I'm gonna try and keep it as just A to the m. That may be more confusing for you, and I apologize. Um, but it's better for me. B is a power of a to the n. Um, okay. Now, what do we want to do next? Um, well, what do we know for sure? We know that G is cyclic, and we're gonna have to rely on that pretty heavily. So let's say since B is in H, um, and H is a subgroup of G, we know that B is in G. That makes sense, right? Hopefully, subgroup that's part of the like identifying features is it's in G as a group. And since G and G equals like A, right? So it's generated by A. This means that B equals A to the n for n as some integer. Yay. So that got us somewhere. We have B equals A to the n. Um, Here comes dun 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 the division algorithm. So Mm. we want to show eventually, like I said, that B is some power of A to the M as in marshmallow. So let's find Q and R. I referenced those earlier at the beginning. Those are the standard ones you use for division algorithm. It's okay if you want to use something different. But we're going to find Q and R such that N equals M times Q plus R. That looks very similar. For, and then this is a part I forgot to write earlier, but for R between um, 0 and M. Note that R can't be M. This is standard because if R was M as a remainder, then it would just end up being a multiple. I could show you this with a basic division problem. But let's say 4 equals 1 times 1 plus 3, right? If this 3, well, wait, that doesn't work. Oh no. I'm not sure. I'm too tired to, this isn't the focus. Uh, Oh, I tried. Anyway, by division algorithm, which we learned last year, maybe I'll do a review on that too. Uh, we know that a to the n equals a to the m q plus r, and that's by just putting a's right here, right? So that should be okay. Now we kind of just have a bunch of like equivalents. So then um, we have oh, I'll just put an equals here. We're gonna like kind of use some power rules. A to the m to the q plus, or no, sorry, times. Ooh, times a to the r. And this should seem good for us because right now, we wanted to show that b is equal to some power of a to the m. And right now we have q being that power. And if you remember correctly, way back when we said that a to the n equals b over here. So we have b equals a to the m as in marshmallow to the q power. We just got to get rid of this pesky little r, or a to the r, I should say. So now let's show what a to the r can equal. And the way we do that is by moving everything else to the other side. By inverses, a to the r equals a to the n um, times a to the m, and then q, or sorry, minus q. I almost said q minus, that is not correct. So we just move this a to the m to the q. That sounds like I'm like wrapping a to the m to the q to the, sorry. um, Okay, so now that we have what a to the r equals, we're going to show, um, uh, oh, yeah, we're going to use that h as a subgroup. Remember, fancy property of subgroups is that they're closed under the operation. In this case, it's multiplication. I almost said under addition. But we know a to the n is in h. We said that earlier. Similarly, we know a to the m in h. So by proxy, I guess I would never say that in a proof, but by proxy, a to the m to the minus q is in h, because this is just multiplying a to the m by itself, negative q times. And since we're making that product, a to the n times a to the m to the negative q, it's closed under multiplication, thus a to the r is in h, which is a big deal because we said something specific about a to the r and a to the m as in marshmallow. By division algorithm, r is between 0 and n. Um, and we assumed m is the smallest integer, right? Smallest integer that is a power, I guess I should say smallest power of a. And if you'll look here, we said that here we let m be the smallest integer in z plus such that a to the m is an h. But we just showed that a to the r is an h and that r is less than m. And so, uh-oh, something broke. Unless, of course, by division algorithm, a to the r equals 0. So a to the r must equal a to the 0, which equals e. And so now if we go back, remember what I said, we had this pesky r up here. It's gone. We showed that it's the identity. So therefore, a to the n, I guess I should, to jump ahead, b equals a to the n. We said that. equals a to the m to the q. So b is a power of a to the m, and we've shown our goal. We've shown that a to the m and we've shown a to the m generates h. We met all of our criterion. We showed all of our definitions, and this is a giant proof. It's a nasty proof. It's an evil one. But understanding it is something even I laugh at the idea of saying that I comprehend all this. But I mean, you get more comfy with it, and you kind of start, oh, okay, I'm sure, and you're getting more comfortable with cyclicness for sure by reviewing this proof. So, thanks, guys. Sorry if I woke you up. I think I'm gonna try and stop here and go back to bed. It's 1:36 a.m. So, yeah.